Hello, welcome to my talk all about fruits. This talk is the second part of the topic on dimensional analysis. In this talk, two very useful examples will be given to show step by step on how we choose the relevant parameters or variables to carry out the dimensional analysis, and how the dimensional analysis could simplify the fluid dynamic problem. The first example is the famous viscous flow in a horizontal pipe. The pictures here are the famous experiment Osborne Reynolds carried out in 1883 in studying the transitions of the flow in the pipe from laminar to turbulent, and he published the paper in 1894 using a non-dimensional parameters first time ever, which was later named as Reynolds number as an indication for the fluid states laminar and turbulent. In the experiment, he showed that when the fluid velocity is small, the corresponding Reynolds number is small, say less than 2,300. The flow in the pipe can be regarded as a laminar flow, and for which an analytic solution can be obtained. It is the famous Hagen-Poiseuille flow. However, when the fluid Reynolds number is increased higher than 2,300, the flow in the pipe would become turbulent, and for such a flow, an analytic solution is impossible. When we examine what parameters might have influence on the fluid friction, from the experience, the fluid might be affected by the following parameters. Fluid velocity. Generally, a larger fluid velocity will cause a large fluid friction. Fluid viscosity could be an important part for the fluid friction. The fluid density might be very relevant for the fluid friction. Generally, for a large pipe, the fluid friction would be larger. And in here, we include the parameters of pipe wall roughness. For a larger roughness, a larger fluid friction may be caused, especially in the turbulent flow. As such, the fluid friction can be expressed as a function as this. So, we have total 6 variables in the problem. The step 2 is to choose the base unit involving in the dynamic system. In this case, and for most other fluid dynamics problems, if the energy or heat transfer is not involved, the base units are 3. They are mass, the symbol m, unit kg, length, symbol L, unit meter, and time, symbol T, unit second. In the third step, the dimensions of all 6 variables are analyzed as in the table. It can be seen that all the variables can be expressed using the 3 base units, and the corresponding symbols for the variables are given as this. In step 4, using the total number of the variables n here equaling to 6, and the base unit m equaling to 3, and we can decide the number of the non-dimensional parameters pi's n minus m equals to 3. That means we will have 3 non-dimensional parameters pi1, pi2, and pi3. In step 5, we are going to construct the 3 non-dimensional parameters as this. Here, 3 independent variables, velocity, density, and the diameter of the pipe are chosen as the constructing variables. But why we choose these 3 variables as the constructing variables? The reason for this, since there are 3 base units in the dynamic system, as we show here, we have to choose 3 constructing variables, no more, no less. For the constructing variables, they must include all the dimensions of the 3 base units: mass, length, and time, and again, no more and no less. When we choose these 3 constructing variables, we can see for the length, L, unit meter, it is the diameter of the pipe with the unit meter. And for the mass, unit kg, it is the density of the fluid, unit kg per meter cubed. It can be given by the rho d cubic. And for the time, unit second, it comes from the velocity, or it is given by d divided by v. After this, the next step would be use the dimensional analysis method to decide the number a, b, c for the first non-dimensional parameter, and d, e, f for the second non-dimensional parameter, and p, q, r for the third non-dimensional parameter. For pi1, it is construct with the fluid friction and the 3 constructing variables. We can make a dimensional analysis by grouping all the base units together as this. The variable dimensions in this table are used. To make the constructed parameter pi1 to be non-dimensional, we can have equations as this. So we solve the number a, b, and c. Thus, we have the non-dimensional parameter pi1 as this. This non-dimensional parameter is actually the friction coefficient Cf. But for a general formulation, d squared might be replaced by the area S. d squared and S have the same dimensions. For the second non-parameter pi2, we have dimensional analysis as this. So we have the equations for the numbers d, e, and f. Solving this equation, we have the solution. D is -1, e is -1, and f the -1. So we have the non-dimensional parameter as this. However, in practice, the reverse of this non-dimensional parameter is generally used. This non-dimensional parameter was first proposed and published by Reynolds in 1894 when he studied the pipe flow transition from laminar to turbulent. And this non-dimensional parameter was later named as Reynolds number, as we are using today. For the third non-dimensional parameter, which is constructed with the paper wall roughness epsilon and the three constructing variables. Using dimensional analysis, we can get the equations as this, and to solve the equation, we can easily get P equals to 0, Q equals to 0, and R equals to minus 1. Thus, we have the non-dimensional parameter pi 3. This non-dimensional parameter is called relative roughness. The original multivariable problem for the fluid friction, we have 5 variables for the function. After the dimensional analysis, the multivariable problem can be simplified as the problem as this. So the non-dimensional fluid friction coefficient is a function of this. Or we have the more practical expression CF. The non-dimensional friction coefficient CF is a function of the Reynolds number and the relative roughness. In reality, there might be a case that the wall roughness might not be a parameter in the fluid dynamic problem. For instance, for a smooth pipe, then the friction coefficient CF would be the function of Reynolds number only, as we have seen in the talk on principle of dimensional analysis as this. This may be the most significant case for the dimensional analysis for simplifying the fluid dynamic problem. In this slide, a Moody diagram is given from the published experimental data for the friction coefficient of the viscous flow in a horizontal pipe. The relation between the friction coefficient and the Reynolds number and the relative roughness can be clearly seen in the plot. From the plot, for the flow in a pipe, there are 3 types of flow. When the Reynolds number is less than 2,300, the flow is generally laminar, and the friction coefficient is given by 64 divided by the Reynolds number, and the pipe roughness has no effect on the friction coefficient. When the Reynolds number is very large, the flow becomes fully turbulent, and the corresponding friction coefficient is a constant, which would be independent of the Reynolds number. However, it can be seen that for different relative roughness, the friction coefficient is different. The higher the relative roughness, the larger the friction coefficient. Between the laminar flow and the turbulent flow, there is a transitional flow for the intermediate Reynolds number. It can be seen that the friction coefficient is more complicated in this region, and correspondingly, the translational flow is more complicated. The second example is the examination of hydrodynamic force on a floating structure in seas under the action of waves. And we will see how the dimensional analysis could simplify the problem. In the first step, we need to identify the physical variables which might have effects on the hydrodynamic force, the velocity of the structure, or the relative velocity between the structure and the fluid. The forces will be relevant with the relative velocity. For instance, the viscous force. The fluid viscosity is the important factor for the friction on the structure. The fluid density may have a large influence on the hydrodynamic force. The larger of the structure, the larger the dynamic force. And the gravitational acceleration might be important in this case because the hydrodynamic force might be caused by the wave, while a wave is a gravitational wave. So G is the relevant parameter. In many cases, the structure roughness is not included in the analysis, since for the well-prepared models, the structure roughness would be carefully controlled, and the corresponding corrections might be well established. As such, the hydrodynamic force can be expressed as a function of 5 independent parameters: V, mu, rho, the L, and the G. So we have total 6 variables in the problem. That is, n equals to 6. Similarly, the second step is to decide the base unit. We have 3 base units: mass, length, and time. After that, we need to make the analysis of the dimensions for all variables, as we see in the table. And the corresponding symbols are given in here. So in step 4, based on the analysis previously, we have the total number of the variables, n equals to 6, and the base unit, m, equals to 3. Then we can decide the number of the non-dimensional parameters for the problem. In this case, n minus m is 3. Therefore, there will be 3 non-dimensional parameters. In step 5, the 3 non-dimensional parameters are constructed in a similar way as we mentioned before. So, because we have 3 base units in the dynamic system, so we have to choose 3 constructing variables, no more, no less. And for the constructing variables, they must include all the dimensions of the 3 base units: the mass, kg, the length, meter, and the time, second. Again, no more, no less. So for the length, it is from the length of the structure. And for the mass, it comes from the density of the fluid here. And for the time, it is from the velocity of the structure. So the step 6 is to obtain the non-dimensional groups, pi 1, pi 2, and pi 3. The process for getting all these non-dimensional parameters are the same as those in the first example. For the first non-dimensional parameter, it is actually the coefficient of hydrodynamic force. And for the second non-dimensional parameter, its reverse is the Reynolds number, as this. And for the third non-dimensional parameter, the corresponding useful non-dimensional number is fluid number, calculate as this. So, for the hydrodynamic force for the floating structure, after the dimensional analysis, the coefficient of the hydrodynamic force can be expressed as a function of Reynolds number and fluid number. So, after the dimensional analysis, the problem becomes much simpler. And we can study the problem by varying the Reynolds number and fluid number, rather than change all the individual variables. From the relation of the hydrodynamic force coefficient and the Reynolds number and the fluid number, we can obtain the hydrodynamic force easily from the hydrodynamic force coefficient. In many practical problems, when the viscous force becomes relatively small when compared to the gravitational force, for instance, the Reynolds number is very large, then the relevant hydrodynamic force becomes independent of the Reynolds number, as we see in the Moody diagram. So, in this case, we have the function as this, which means the hydrodynamic force coefficient is the function of fluid number only. This relation is the principle used for physical model test in the tank.